Hello everyone. Today I'm going to talk about Huoyan, accuracy, scalability, coverage, a protocol configuration verifier on a global WAN. I'm Fangdan Ye from Tsinghua University, and this work was done when I was an intern at Alibaba Group. This is joint work between Alibaba Group, Tsinghua University, Brown University, and Nanjing University. As one of the largest service providers, Alibaba has a global network infrastructure to serve over 1 billion customers worldwide with its online services, such as cloud service, e-commerce, e-payment, online maps, and so on. Maintaining the configuration of Alibaba's network, especially our global WAN, is extremely challenging, because our WAN not only contains a large number of routers, IP prefixes, and links, but also involves multiple protocols, including BGP, IGP, static routes, as well as ACL rules. In order to prevent the incidents resulting from network misconfiguration, Alibaba decided to adopt network verification techniques as an automatic and systematic way to proactively audit our configurations and prevent configuration-induced incidents ahead of time. Our verification system is named 火眼金睛. This name is from the skill of the Monkey King in ancient Chinese myths, which means the Monkey King can see the truth through his fire and golden eye. In SIGCOMM last year, we have presented our ACL verification work, 金睛. Today I'm going to talk about 火眼, the routine configuration verification system. Building our verification system requires us to address multiple practical challenges. The first challenge is our WAN consists of routers from different vendors, which have very different vendor-specific behaviors. For example, one same configuration command, like removing private AS in vendor A, may mean removing all the private AS numbers, but in vendor B, it may mean removing only private AS numbers until the first non-private one. Even the most knowledgeable operators cannot grasp all these vendor-specific behaviors. The second challenge is our WAN contains a huge number of devices, links, and IP prefixes, and the topology is not symmetry, which invalidates any existing symmetry-based approach on our network. The third challenge is this one employs multiple protocols, including BGP, IGP, static route, and ACL rules. So many protocols are tangled with route redistribution and numerous routing paths, giving rise to complex logical route reachability relations in the network. Finally, links and routers in our WAN fail commonly, and there are also non-deterministic routing arrivals in our network. Before I show you how we build our verification system to address the above challenges, I present our goal and design insight based on our operation experience. What capabilities our operators are interested in. As shown in this table, our operators list 6 key properties for verification and classify them into 3 groups. Mandatory property means these properties are the most essential to make the verification applicable to the WAN. It includes scalability, correctness, and protocol coverage. Preferred properties represent features that are very helpful, although they are not fundamentally necessary. The optional property can be given up to make the verification more lightweight or easier to realize. We want to extract a design insight to meet these properties, especially mandatory and preferred properties. We analyzed and tested the state-of-the-art solutions, like Batfish, Minesweeper, and Tiramisu in our network to see their performance. In general, we noticed simulation solution like Batfish is scalable in large network, but is very slow in handling preferred properties, such as k-failure tolerance verification. On the other hand, we notice formal model solution like Minesweeper can handle preferred properties well, but is not scalable to our large network. Therefore, Huoyan is designed as a global simulation and local formal modeling verification system. Huoyan is primarily a global simulation-based verifier for mandatory properties, and also a local formal model verifier for preferred properties. Huoyan has been used in our WAN for about 2 years. Huoyan mainly focuses on 2 types of verification tasks: online configuration verification and configuration update verification. The former means Huoyan checks the reachability properties of online devices in runtime, and the latter means Huoyan is used to check whether updated configurations may violate properties of interest ahead of time. Let me show you the online configuration verification workflow. First, the operator queries Huoyan for her verification purpose. Second, Huoyan loads online configurations and generates network behavior models. With the network model and verification intent in hand, Huoyan reasons about whether the network model meets the input property. For the update verification case, the operator sends the update plan to Huoyan, and Huoyan simulates the updated network model. Finally, Huoyan checks whether this updated network model meets the property of interest before the update task commits to the network. If the update can case misconfigurations, the operator is able to get the result from Huoyan ahead of time. In order to ensure the correctness of network behavior model, we also equip Huoyan with behavior model evaluator to tune the network model in a periodic way. The gray part in Huoyan architecture is called model tuner, which is responsible for ensuring the accuracy of generated behavior model. The design of model tuner is our first innovation. The rest part is called config verifier, which focuses on reasoning about the configuration correctness in a scalable way. This is our second innovation in Huoyan's design. In the rest of my talk, I will show you the design of these two parts in details. Let me show you how we build the model tuner. Model tuner aims to detect vendor-specific behaviors for the accuracy of our behavior model. Let me show you why a vendor-specific behavior matters. In this example, we have 4 routers. Router 1, 3, and 4 are provided by vendor A, and router 2 is from vendor B. Suppose 2 prefixes, 10/8 and 20/8, arrive. R1 adds the community to them and sends them to R2. R2 keeps the community, then comes R3. R3 tries to add community to prefix 20/8, but finds it already exists. Finally, R4 accepts both of the prefixes and generates the routing table. Unbeknownst to us, R2 in reality is from different vendor from R1, R3, and R4. It has a latent vendor-specific behavior which removes community of BGP updates. In this case, 2 prefixes arrive. R1 adds the community to them and sends them to R2. R2 drops the community, then comes R3. R3 adds community only to prefix 20/8. Finally, R4 only accepts prefix 20/8. We eventually get a different routing table in reality, which is different from our simulation result. We build a device behavior model tuner which uses production network as a reference for our debugging. The key challenge here is how can we detect VSBs? As shown in this example, the model tuner periodically connects real-world routing tables and checks the difference between the real-world routing tables and simulated routing tables in order to find the difference. Our intuition is once a difference is detected, say R4's routing table, the tuner backtraces the path until a router whose routing table is the same, say R3 in this example. So the VSB must be in R3's egress policy or R4's ingress policy. Unfortunately, using normal RIPs cannot localize the correct VSBs in practice, since normal RIPs lack of a lot of useful information for the reference. Therefore, our tuner uses extended RIPs rather than normal RIPs. After we introduce extended RIPs, we can observe that the tuner can correctly detect R3's extended routing tables between real and simulation are different. So this VSB exists in R2's egress or R3's ingress. Our model tuner successfully detected 8 VSBs by far, including default ACL, root policy, removing private S, and so on. These VSBs significantly affected the accuracy of Huoyan's verification results at the early stage of Huoyan usage. As shown in this picture, before we detected these VSBs, the accuracy of our verification is below 50%. But after used our model tuner 6 months, The accuracy of Huoyan has been near 100%. Let me show you the second innovation of Huoyan, the scalable method to reason about the network properties. The key challenge in our verification design is how to reason about k-failure property in a scalable way. K-failure property means whether the reachability holds if arbitrary k-links or nodes fail. This means whether the current network is robust enough to tolerate one or more link failures. Let me show you two examples to illustrate what is k-failure problem. In the first example, k should be 1, because if the link between D and E fails, the original reachability no longer holds. In the second example, k is 2. This is because if these two links fail, the reachability is violated. However, reasoning about the k-failure property in R1 is very hard. First, it is time-consuming if we enumerate all the possible failure cases. This is also the reason why existing simulation verification systems like Batfish are not scalable in k-failure property reasoning. The second reason is R1 is not symmetrical, so the existing reduction and simplification approaches like bonsai do not help. Now let me show you how do we design our verification algorithm for the k-failure property reasoning. The key design for scalability is a global simulation and local formal modeling approach to reason about the reachability. Let me show you one simple example. In this example, we have 4 routers, A, B, C, and D. Each of them belongs to different AS domain. Every link has a unique ID. Router A is a BGP announcement node which announces a prefix 10/8. In this example, we aim to reason about k-failure reachability where k is equal to 1, which means whether the reachability of this network can tolerate arbitrary one-link fault. First, A announces the prefix to C and appends the link ID A1. Then C updates its RIB. Next, A announces the prefix to B. Then comes C, with A2 and A3 appended. C makes a route selection and finds R1 is the best route, so it can be directly ready to send to D. R2 is the second route, so it can be sent out if and only if R1 doesn't exist. Finally, C sends the 2 updates to D, and D updates its RIB. By far, we have finished the entire verification process. We can use SMT solver to get the result that k is equal to 1 in this network. Because if A4 is down, the reachability does not hold between A and D. To make the algorithm scalable enough, we optimize this algorithm by the following ways, like dropping more than k cases, dropping impossible cases, and simplifying logical formulas during the simulation process. In addition, Huoyan can run the above simulation for different prefixes in a parallel way. By far, we have learned how does Huoyan achieve accuracy based on network model tuner, and how does Huoyan achieve scalable k-failure tolerance verification for BGP protocol. For the rest part, for example, verification algorithm for IGP and non-deterministic routing racing, please see our paper for more details. Huoyan has been used to verify our configuration online in a periodic way for 2 years. During the 2 years, it detected many potential configuration errors hiding in our network. Main configuration errors we detected include IP address conflicts, bottlenecked link and device, as well as redundant device misconfiguration. Huoyan has been used to verify our configuration update plans ahead of time for more than 1 year. In 2019, it detected many potential configuration errors in our update plans, preventing outages before failures occur. Because of Huoyan's verification, the outage number of Ali Cloud significantly reduced by comparing with the previous years. Let me show you one real and tricky misconfiguration case Huoyan detected in R1 that most of existing verification systems cannot detect. In this subnetwork, there are 4 routers. Router C announces a prefix to A and B. This BGP update's local preference is 300 and weight is 0. In addition, router D also announces the same prefix, but its local preference is 500 and weight is 0. Router A has a local egress policy that can change the weight of BGP updates from 0 to 100. This case is tricky. If C's BGP updates arrives B before D's BGP update, then the weight of C's BGP update is changed to 100. Thus, D's BGP update is dropped, because its weight is 0 lower than 100. So the next hop of this prefix in B's routing table would be A. On the contrary, if D's BGP update arrives A before C's BGP update, then the weight of both BGP updates are the same. But because D's update has a higher local preference than C, C's update is dropped. In this case, the next hop of this prefix in B's routing table would become D. Such a tricky misconfiguration can cause non-deterministic routing tables, thus violating our operator's network connection expectation. Existing efforts like Batfish and Tiramisu cannot detect this misconfiguration. Huoyan introduces an algorithm to check such non-deterministic case in real world. We evaluated Huoyan in our entire WAN by verifying all our thousands of prefixes. To finish the entire verification, Huoyan spends about 8 minutes in the regular case. By considering failure case, Huoyan needs more time but still acceptable. We also try to run the existing verification systems like Batfish, Minesweeper, and Tiramisu in WAN in order to verify the reachability properties. Good news is these systems are runnable in our WAN directly, but bad news is we fail to get any results back within 20 hours. But in order to compare our system with the state of art, we chose several subnetworks in our WAN to run the evaluation. For instance, this table shows the comparison result of Huoyan, Batfish, and Minesweeper on a small subnetwork with 20 routers, each with thousands of configuration lines. We can observe that in the regular reachability verification, Huoyan and Batfish have similar performance, but Minesweeper is much slower. Under K-failure tolerance reachability, Minesweeper is better than Batfish, but both of them are much slower than Huoyan. Then we chose a medium-sized subnetwork to compare these systems. This medium-sized subnetwork contains 80 routers, each with thousands of configuration lines. We fail to get results from Batfish or Minesweeper when we try to reason about the K-failure tolerance properties in this subnetwork. We have more evaluation results, such as formula length of our encoding, the turnaround time for checking one IP prefix, and the effectiveness of pruning optimization with different K. Please see our paper for more details. In conclusion, Huoyan is the first ever reported practical configuration verification system deployed on Alibaba's global scale WAN. It addresses the challenges on accuracy, scalability, and coverage. Huoyan has been used to verify Alibaba's WAN for 2 years and significantly reduced the number of outages in Ali Cloud. This is the end of my talk. I'm happy to take any questions. Thanks.